there's one more very important concept that we haven't talked about yet, and we need to think about it before we start making calculations of the membrane potential for the whole cell. So now we can calculate individual ions' equilibrium membrane potential using the Nernst equation. But their contribution individually to the overall membrane potential of the cell is dependent on how permeable the membrane is to each ion. Permeability is the ease with which ions can pass through the channels and through the lipid bilayer. An ion with higher permeability, like potassium in a real neuron, can pass through easily. High permeability can be caused by a greater number of channels, or by channels that allow ions to travel more easily through them. This is like having a lot of doors in our Fleet Week example, or a door with a very lenient bouncer, friendly with the British sailors.
The GHK equation, named after the scientists who derived it, David Goldman, Alan Hodgkin, and Bernard Katz, helps us calculate a more realistic membrane potential. It puts coefficients for permeability in front of the major ions that contribute to the resting potential in order to weight their relative effects.
There's a subtle difference between the Nernst and GHK equations. Unlike a Nernst potential, which describes an equilibrium where the net efflux and influx of ions are equal, the GHK equation represents a steady state rather than an equilibrium condition. The difference is subtle but important. An equilibrium occurs when the net action of two processes cancel out. If our membranes were only permeable to potassium, then the resting potential would be an equilibrium potential. That is, the system would reach a balancing point where the concentration and electrical gradients exactly balanced out, and the system could, in principle, stay that way forever. However, as we mentioned earlier, the membrane is permeable to other ionic species, and even a slow leakage of sodium into the cell will eventually erode the resting potential. The sodium-potassium pump keeps that from happening, but because this is a dynamic, energy-consuming process, we can't say that the system is at equilibrium. It is, however, at steady state, which is to say the concentrations are stable and steady, even if there's quite a bit of movement behind the scenes. So now you hopefully have a good sense of what's happening in a resting neuron. Let's take a moment to understand in greater depth the differences in interpretation between the Nernst equation and the GHK equation. One key difference that we touched on earlier is the concept of permeability. Why does permeability matter?
Remember that the Nernst equation only describes the equilibrium state of a single ion, but the resting potential is formed by the contributions from many different ions. So one way we might imagine to calculate the resting potential for a whole cell would be to simply sum up the contributions from each ion's Nernst potential. But we already saw how important the selective permeability of the membrane to particular ions is to maintaining the resting potential. Not all ions are equally permeable across the membrane, and we need to take this into account. Sodium, for instance, has a positive Nernst potential, and thus experiences a strong inward driving force. However, in spite of this potential drive, sodium isn't allowed to rush across the membrane, because there are very few open sodium channels in a resting membrane. Thus, we say that sodium has a low permeability at rest. Potassium has a much greater freedom to diffuse across the membrane at rest. We say that it has a much higher permeability at rest. So, since the permeability of the membrane to sodium is very low, the term P and A is close to zero, and thus the effect of sodium concentrations on the resting potential is small. As you might imagine, the greater permeability of the membrane to potassium ions means that potassium has a greater influence on the membrane potential. As a result, the resting potential is much closer to potassium's Nernst potential than it is to the Nernst potential of sodium. Looking at this equation, we can even see that if we restrict movement across the membrane to a single ion, say potassium, by making the permeabilities of sodium and chloride be zero, the GHK equation reduces down to the Nernst equation.